Welcome, guys. So in the previous video, we already talked about cone and cocone. Okay, so let me quickly remind you guys that cone is something map out, and cocone is something map in, and the limit and colimit are just the limit and terminal object in the cone, and the colimit is initial object in the cocone. Okay, so today we are using these two ideas, the colimit and limit, to construct a lot of categories objects. Okay, so I would say this is the constructions in categories. Okay, so there are lots of so we only talk about some common one, which the first one is trivial. It's the easy one called the product and coproduct. Okay, and the second is the I should say the equalizer. Okay, so it's so hard to spell, equalizers and the coequalizers. And also famous in the algebraic geometry or other algebraic topology is pushout and pullback. Yeah, I mean, pushout is in the fundamental group if you learn about the algebraic topology, and the pullback is also in the algebraic geometry. Yeah, these are all something which is non-trivial. And in the next video, we will talk about zero morphisms. Okay, and also there's some ideas, image and a co-image. Okay, so yeah, so let's start. So just an introduction. So right, so it should be so up to here now is easy. So let's talk about the product. Okay. So remember, okay, so I can define a product as a limit of a diagram, right? What kind of diagram? Just A and B, right? I don't add, there's no arrow. Okay, so this is the definition. Okay, but maybe you guys don't understand, so let me just write down. So okay, so now the product means that there is a P. So given two objects in a category, there is a P and the list pi1 and pi2. So remember that I use this color means that this is the products. Okay, so these P and these two are the products, right? Remember this is the object in the cone, right? So in the cone, you need to have some object which map out to the other two, right? So cone, so this is a cone. Okay, so these P and pi1 and pi2 are objects, also are products such that which is a terminal, right? So such that if any x map, let's say if you have x and map to x1 to A, x2 to B, then there will be a unique. Let me just change the color, keep to make it U, right? Such that there's uniquely U. So this U thinks the universal property, so it must be unique. Yeah, I mean there's a unique U, and by this unique U property will make these products unique up to isomorphism. Okay, so I say again, these P and pi1 and pi2 are product cells. So products not just objects, which must contain two map. Okay, so this is product. Okay, so let's define a coproduct. Right, so you just dualize. Well, you get oh, by the way, the diagram need to commute, right? So you need to commute. So U pi1 U need to be x1 and the pi2 U need to be x2. Okay, so I mean you can dualize, right? Dualize that just change all the arrows. So the coproducts. Okay, so I should use Q, right? So let's make the color. Oh shit. Okay, so Q, right? And the pi1 and pi2 should be here. And then you also you still have A and B, right? And this coproduct means that there is a map. If you have X, right? So now you have X. All right, bro. Which if you have A1 map to X1 and made to B map to X2, then there is a unique morphism from Q to X. Right? You need to change the change the notation, change the arrow, right? So unique. Okay, then this is called the coproduct. Okay, so product is also obvious. This is just a co-limit of A and B, right? So now you see you now see the powerful idea of the cone and cocone and the limit co-limit, right? Because you have the idea of cone and cocone, then you can construct a lot of small powerful objects. Okay, I think I don't have to talk about examples, but there is a theorem that I will not prove. I just leave as exercise. Okay, so it's easy. Just the A, B product BC. Oh, by the way. This is isomorphic to A, B, C. Isomorphic to A, B, and C. Okay. And also, yeah, that's it. Oh, by the way, yeah, this is the product. Okay, and some people use addition as a coproduct. Okay, so you can also check that per coproduct is associative. Okay, so if the product and the coproduct are the same, then we call it biproduct. Okay. Okay, so biproduct definition means that it is both products and coproducts. Okay. Okay, so up to now, we finished this. Let's talk about equalizers and the coequalizers. Okay, so still the same technique, right? We build some stupid diagram and we construct the co-limit, right? So my idea, so let's talk about equalizer. So if I have A and B and the F and G, so notice that now diagram looks like this. Okay, so A and B and the two maps. Let's define. So equalizer means that you have a map E, you have object E and this E. So these colors are so this E and this small E are equalizer. Okay. And also we have some property, right? Such that we must have F E equals to G, such that if you have any Z, let's say this is large Z, small Z mapped to large Z and morphism Z, such that F circle Z equals to G circle Z, then we must have a unique, right? A unique morphism, which send in, right? So send in. Okay, so such that our diagram comes in. So basically, this is the unique morphism. So these are equalizers such that if any object which satisfies property, it can map in, right? So this is viewed as it's also somehow like the ideal limit and co-limit. Okay. Okay, and let's see. Yeah, so let's so this equalizer is easy to build an example. So let's say example. Oh, by the way, I don't want to write, but you can dualize. You can dualize it. You get if you have A and B, right, and F and G, and then if there is a map, if there is a something object Q here, you map to here. This is called the coequalizers. Okay, so let me just give you an example of the equalizers. So let's see, you can define a set. So let's say A and B are both set. Yeah, so now we are working in the set categories. So set category. So set categories that each object is a set and the morphism just a map from two sets. Okay. So let's define E to be x belongs to A, such that f of x equals to g of x. Right, so this is stupid, right? This is the if you have two sets, then what is the equalizer of A just should be viewed as a subject, right? So E in this case, E is monomorphism, right? So E can be viewed as a sub-object of A, right? So E is and the map just the inclusion. Okay, so this is the equalizer. Okay, so it's very so you see in this case it's very intuitive that you guys know what's going on. Okay, another example is that let's work in the groups, right? So in the groups, equalizer of the equalizer, let's say if you're G and H, right, and you have a homomorphism phi, and then you go with the trivial homomorphism 0 to 0 GH, right, and the equalizer. So I think everybody can guess the answer, right? Equalizer is it maps the same, right? So this must be a what kernel, right? So just kernel. Okay, so these are easy, and then co-equalizers, it's also easy. So let's see. Yeah, in a set that the co-equalizer, let's say the if you have these two map G and B in a set, so co-equalizer should be viewed as the object, right? Mapped out, and this map should be surjective, right? So actually, coequalizer is just a B modulo something, which is this modulo means that if X and so we need to, so this modulo means that in the equivalent class means that f of X the same let's say view as equivalent as G of X, right? So this is a surjective map from here. Map B map to the quotient. Yeah, so this is a set. And if you work in a groups, then this should become a cokernel, right? So this is kernel, this will become a cokernel. So this just shows that the ordinary equalizer and the ordinary kernel and cokernel idea just become equalizer and coequalizer. Okay. Okay, so then finally, let's talk about pullbacks. Pushout. Okay. Okay, so I mean I don't know what you guys knows about these pullbacks or pushout. So let me just give a tip. So let's talk about pullbacks. Okay. So pullbacks means that if you have a set which A, B, F, and G. Okay, so now these are your diagram, and let me just change the color to say what's the pullback. So pullback, you need to push this F and G back, right? Back is in the off diagonal of sorry, these directions, right? So let's see. So if you have P here, and then you need to give us a two map, right? Such that this is P1 and P2, such that if you have any object here, right? Let's say this is Z, map Z1 and Z2, make this diagram commute, then there will be a unique Z to P, such that everything commutes. So as I said before, this P and the P1 and P2 are objects, are the pullbacks, right? This is you should view this as cone. Okay, then the universal property will make it into the cocone, right? Because any object need to map into P. So because P should be viewed as a terminal object. Okay, so another definition is that which is a little bit abstract, that the pullback just the limit of this diagram. Right, so you build a cone and you build a terminal object. Okay, so and then you can dualize. Right, so dualize you get a push out. Right, so if you have a, let's say you have A, B, and C, and G, and F, or you can define a let's see. Yeah, I mean you can define a push out, right? Just push out should be here, right? And yeah, so these two are push out, right? Such that if you have any morphism here, this commute, then it must stand out to be here. Okay, I think this is just simple exercise for you guys to check what hell is going on, right? But just a definition. Okay, so let me so if I remember correctly, so let me just give you the example. So I remember that the push out, right? So push out is showing the algebraic topology. So algebraic topology. Okay, so there is a thing in the algebraic topology called the fundamental group. So given a topological space X, you can consider all the paths start from X0 and finish X0s, and use a homotopy as an equivalent relation, then you can construct a group called fundamental group. Okay, but in a category sense that the fundamental group is just a functor, right? But The idea is that if you have two space X and they just hit the point Y, right? And or basically you can, or basically one result is that people like to compute this space, the fundamental group of this X cross X and Y, right? So this should be like as I forget what I remember it's wedge. Okay, so yeah, if I miss that, you just comment. Okay, so this X wedge Y just the free product of X and Y, right? So free product means that free product means that you can construct you can say this element is A, this element B, and then so AB is not the same as BA. So we can construct A squared B, A, B, B, A. So they're all different, right? Because you only hit the point, right? So you cannot cut this point. So if you go left and go right, it's not the same as you go right and go left. Okay. But what I'm saying is that what I'm saying is that in general, if if you know the pi 1 x intersection y, then you should be able to compute the general in general situation if their intersection is non-trivial, which the final result will be the Van Cappen formula. So there is a thing called the Van Cappen, such that let's say this pi 1 total space Z. So you will construct a map. There is a, is it correct? Yeah, I mean, okay, sorry, I forgot. Yeah, but I remember the results will be just the push out of the fundamental group. Well, forms the so basically the Van Cappen formula is just a push out of fundamental groups in a category sense. Don't worry. Okay, so for this session, I will provide the actual idea. So I need to check. Okay, so yeah, hope you guys like this video. So in the next video, let's talk about zeromorphisms and kernels. And after that, we will talk about Yong-Lee lemma and sheaf and presheaf. Sheaf and presheaf, I just want to quickly give an idea. And the final, we talk about a fundamental group and the broad fixed point theorem. Just a quick introduce why category is important. Just a very simple idea. Okay. By the way, category is a very hard subject. But there is an abstract technique that I think is very interesting.